Okay.
Okay, I have shared my screen. Okay. So we have discussed this part of random forest last time. That yeah, multiple decision tree we will use in order to uh, confirm, or you can say with more confidence, we can say that this is the particular label for the data, for the test data. The other part which was there in random forest was random selection of features also. So that was just to fasten the process, so that at any time while splitting, when you say, see, first thing is you split on some feature, right? Some feature you split that, okay, if the value is greater than this, then I will go this side or that side, whatever it is. So, but then random forest, what people did, people said that anywhere while splitting, we will use random selection of features too. Like if you have 15 features, we will randomly select 5 only, and on that we will calculate the information gain and those Gini index and information gain, and whichever feature will be best for splitting, whichever feature will give us more information gain, that we will choose for splitting. So majorly these two things were there in random forest, which makes random forest quite popular and a very effective model, because you are relying on more models now. Also, a single model, a single decision tree model may be sometime get overtrained, or it becomes very complex to comprehend. Okay, so then also random forest was used. Today we are going to start with a new model which is also based on decision tree only. I mean, the basic, the foundation model is decision tree only, but this is a new model called as gradient boosting. What is it called? Gradient boosting. So this is another model which we are going to study. Now, just before starting, I just want to emphasize on one thing with random forest, and that is, random forest you can independently train the decision trees. If you have understood the random forest, you can easily conclude that once the multiple data set has been created by randomly choosing say two-thirds of the data, the big data, you can randomly choose say 10 data sets. You can randomly create 10 multiple data sets from the bigger data set, right? And then on those 10 data set, you can independently train the decision trees. So 10 decision trees you can independently train. Now, that was independent training. I mean, you can parallelize that. If the training could be made faster and everything. Okay. Now now talking about gradient boosting, I will introduce this model first. First of all, you need to understand that gradient boosting over decision trees. This model is a sequential model. It is not independent trained models. Again, gradient boosting also uses decision tree, and gradient boosting is over decision trees are also a group of decision trees working together. First, you need to understand this. Like random forest, gradient decision boosting also have multiple decision tree in place.
Hello.
Yeah, yeah, hello.
Yeah, your voice is breaking just now. I
Okay,
don't know how.
okay. So what I was telling is gradient boosting. I will introduce gradient boosting to you. Gradient boosting is a sequential model. First of all, you need to understand that gradient boosting is also a group of decision trees. like random forest. Okay. Now, like random forest, it is also a group of decision tree, but the training, how you train the model, that differs between gradient boosting and random forest. In random forest, I told you the decision trees can be independently trained over the multiple data sets. Here, in boosted decision trees, it's a sequentially training process. It's a sequential training process, and you do not divide the data set. No, you never divide the data set. If you have a say 20,000 or 50,000 data, you keep it like that only, 50,000 data or 10,000 data points, whatever it is. The data set is not divided on the whatever data set is given on the same data set. That thing is done like 80-20 and all. I mean 20% you keep it for testing. Whatever 80 is left on that 80, that 80 is not further divided. Remember that 80 data
Okay.
sets, that 80% of data set will be there. Now on that, a sequential training of decision trees are done. Okay, and this results in a very high quality model. Why I am saying high quality? I mean this gradient boosting is also one of the powerful models, because the way the training has been done, the way the training methodology has been developed, it is very good. I mean I will tell you, you will understand what actually gradient boosting does. Okay. So gradient boosting is basically boosting algorithm. Boosting class of machine learning algorithms are totally all a different family. Here on decision tree, this boosting algorithm is applied in order to increase the accuracy. So this was proposed in 1996.
Hello.
Uh, okay,
Sorry. Uh, Hello.
yeah.
Again, I'm completely missed the last sentence.
Okay. Yeah. So what I was telling is, boosted decision tree was introduced in 1996, and this boosting is completely a different family of machine learning algorithm altogether. Here, boosting is applied on decision trees in order to
Okay.
give better performance, better results, better accuracy. Okay. Now, coming to the how this boosting, gradient boosting over decision tree work. So there is a saying, in machine learning, that instead of trying to make a very good, strong model, what you can do is, if you have lots of weak models, you can combine them in such a way that they become a strong model. So some weak learners also you can combine in such a way that they become a strong model, a powerful model.
Okay.
So that's what gradient boosting does. Now how it does, I told you, you are not going to divide your data set. Whatever data set is there, you will keep it as it is. Unlike random forest, the data set is not divided. Remember, in random forest, the data set is divided. Here we are not going to divide the data set.
Yeah.
And you see what it does. Weak learner here is decision trees. Because as I told you, this model is gradient boosting over decision trees. Okay. So this is weak learner, here is decision trees only. And you say, what is this? X1, X2, Xn. These are what? These are basically the feature vectors, the data points. These are the data points.
Data points.
Yeah. And these are the labels y1, y2, y3, like that. Okay, yn. And now these are the weights which are given. These are the weights which are given. I mean, till now, whatever machine learning you have learned, you would have not found, you would have never found basically this weights kind of thing in the data. What we have seen,
Yeah.
we have seen a lot of data points and their labels. Everywhere there are data points and there are labels, right? Weights are never there.
Right.
But in gradient boosting, what it does, I told you it's a sequential process. Initially, you take your data point and the labels and you train a weak learner, you train a decision tree on that. Okay, you train a decision tree on that. Now, this is a decision tree which has been learned. Now, you see, that's the general, this is the general thing, okay, this is the general funda. You have these data points and you have these labels. So given the data point, it will tell you the what is the class y1, y2, y3. What is the class? Setosa, Virginica, versicolor. What will be the class? Okay, given the instances. Now, how boosting is done? This is actually I just wanted to show you what is a weak learner. So basically, this weak learner is nothing but a decision tree. This thing is a decision tree only. Okay. And this is my data point x and y, which I am feeding it to decision tree, and it has learned a tree. This is a tree. So on that tree, if you give any data point d, it will tell you the class, isn't it? By I mean, see, this is what, this is something like this, right? So if you give x1, x2, x3, xn, it will go down, go down, go down, go down, and it will may lead up to here. Whatever class will be there, say Setosa will be there, so it will say that it is Setosa. Just an example I am telling you. We have seen how on test data decision tree can make classification, right? Now what I just wanted to know is, oh sorry, yeah, boosting process. How this boosting is done actually. See, this is a very interesting process. Uh, you will see. See, first of all, learn one decision tree on all the data set. Whatever data you have, just learn a decision tree, and to each and every point, whatever data you have used for learning. Say, suppose you have 10,000 data points. So all the data points are given equal weightage. All the data points are given equal weightage. You just think that weight is something which is initially equal among all the data points. Now you have learned a decision tree. Now this decision tree will be 100% accurate. Do you think so? No, because decision tree has their own limitation, right? You cannot say that any data set you train a decision tree and it will give you 100% accuracy, right? So maybe the decision tree will be not that accurate. So that's a weak learning basically which is happening. Now initially what I told, each and every data, all the 10,000 data points have got equal weightage. This is the first iteration. Now in the second iteration what will happen, again the same data set. See, our first learner, first decision tree, when you learned it through the data set, first decision tree, then you know that this decision tree is giving me say 60% accuracy. So still on 40% of the data point, it does not perform well. Your decision tree, it doesn't perform well. So what boosting does, on those data on which the first decision tree was not able to perform well, will be given more weightage now. And the data points which are very well, all the data points which are very well classified, the 60% data, they are given less weightage. So in the second iteration, when the decision tree is getting learned, Just try to understand. When in the second iteration on the same data D, when the decision tree is going to learn, the second decision tree knows that these 40% data points has, I have to give major focus on this 40% of data set. I have to give major focus on, I have to emphasize on this 40% of data set which has more weightage. Because the rest 60% are anyway, classified by the first tree only. So second tree will be more concerned about the 40% of the data points which were not able to classify. Similarly,
But what
like
is the
that,
decision factor?
yeah.
What is the decision factor to give us preference for this 30%
Okay. So that
over
is given,
60%?
yeah. Yeah, you say? Yeah. So that is given on the training data
Uh,
only.
okay.
Yeah. You are saying something?
Decision factor about uh,
Okay. So
preference on
suppose,
60%
yeah.
of data.
So suppose you have trained your data points, say 10,000 data points for a decision tree. You train the decision tree over that 10,000 data set. Okay.
Uh,
Now, what I
again,
done,
sorry, but uh, hello,
yeah,
hello.
yeah. Please say.
Sorry, but again the voice is breaking.
Okay.
Hello.
Okay. Yeah. Hello. Can you hear me now? Can you hear me now?
Yeah, your voice is break. Your voice is breaking. Yeah.
Yeah. So what I was saying is, say suppose you have 10,000 data points. Okay.
Yeah.
You train the decision tree on that with say 5 depth. Okay.
Okay.
So do you think that decision tree, that weak learner will be able to perfectly classify all the 10,000 data points at leaf nodes with depth equal to 5, because we do not want to overtrain our decision tree. So with depth equal to
Yes.
5, do you think that on the leaf node we will always get the pure results, there will be no misclassification at all? It does
I
not
can't
happen actually.
100% sure.
Huh?
Yeah.
Yeah,
I'm
it
not
does not.
100% sure whether I can get.
Yeah, it does not happen actually. That we have also seen
Mm.
before. That if you fix
Yeah.
your depth, say till you fix till 5, you kept the depth 5.
Hmm.
So there will be there will be lot many data points in 10,000 data points, which is a basically data set. There will be many points which will not be able to get pure Gini index 0, with pure classification. They will be misclassified. Maybe on the leaf node you will get something like 4010 or say 120, something like that. So there will be some misclassification. Those misclassified data will be more emphasized in the second iteration. Those misclassified data will be given more weightage in the second iteration. That's what I was telling. And like that, from each iteration to next iteration, you keep on adjusting the weight, giving more weight to the data points which were misclassified in the previous iteration, giving more weight to the data points which were misclassified in the previous iteration, and little bit
Okay.
less weight to the data points which were easily classified in the initial previous iterations. Okay, like that you will go on doing, you will go on training various decision trees. Again, a group of weak learners you are training here, H1, H2, H3, like that. Sequentially you are doing that. Say 10,000, you train a decision tree, give more weightage to the misclassified data points, Again train a decision tree. Now you have two decision tree. Again give more weightage to the misclassified one. Again a decision tree. Like that, you can train numerous say 10 decision trees, which I mean in sequence, where each one is rectifying the errors of previous decision tree, trying to rectify basically by giving more weightage to it. Okay. So
Okay.
the final model which comes as a conclusion after the training is this. So you take H1, you give it some weightage. Then H2 some weightage, H3 some weightage, H final HT some weightage. So basically this H1, H2, H3, H4, H5 till HT is what? It's a decision trees. These
Okay.
are the decision tree in different iterations. But each one of them are having different weightage. Okay. And this is
Okay.
how a boosting training goes on inside the library. I mean, you will be using the direct library for this, um, maybe in sklearn or whatever when you will be coding. Okay, and you will be just calling the library, but yeah. So, but what I am trying to say is this is what is happening inside. I will show you in fact how it goes on and how the trees are formed. But this is how it goes. Okay, I will also show you again. Yeah, this is again a boosting process. So you have the training set. You can see in this PPT. You have the training example, right? Now this training sample, this is classifier 0. Now whatever misclassification is there in classifier 0, you will readjust the weights. Again classifier 1. Again adjust the weight, classifier 2. Adjust the weight, classifier 3. Like that. And you will finally find the classifier M. Okay. Now,
Okay. Okay.
yeah. So now basically this is how you are going to decide. Each of these classifier, what is this classifier by the way? This is just a decision tree. So each of these decision
Decent.
tree having some weight, some lower, all the classifiers. I mean whatever 10 decision tree you have so all the 10. And what is this C0x, C1x, C2x? What is this? This is basically the result of the decision trees. The result of the decision tree multiplied by the weight, and then you sum it up over all the classifier. Okay, and then you say that okay, this is my answer. This is my label. This is my result. Okay, so
Okay.
this is how boosting is done. Two different. Okay, these are just the theoretical part, that how this class, finally the class is chosen. So this is the final classifier formula that I showed you in the previous slide. Summation over all the classifiers, all the decision trees which were trained in the iterations, and with some weightage, you have to give, and whatever the tree is giving, that result you have to take. Okay, so this is majorly what boosting does. Okay, you must be
Okay.
able to differentiate between what random forest is doing and what gradient boosting is doing. Random forest is basically creating multiple data sets. Here you are not creating multiple data sets. Instead, the same data you are going through sequentially. There the decision tree training is independent, or I mean you can parallelize them. Here, the decision tree training is a sequential process which will always need the inputs from the previous decision tree. Okay, so
Okay.
and it's all about the adjusting the weights and all. So there are algorithms for that which adjust the weight. There are algorithms made which will adjust the weights in such a way that the error, the misclassification will be minimized. Okay, so this is all about boosting. You got the concept, got the idea of gradient boosting?
Yes, yes.
Okay, great. So what I will do, uh, dt, I will show you. We will do some Python program now. Okay.
Okay, okay.
Okay. So this is a database. This is a data set I have downloaded from some UCI machine learning repository. This is called a wine dataset. In wine datasets, there are basically three types of wine, and your purpose is to identify which wine is this. Okay. So the first column itself tells the class. The first column itself tells the class, and this one first, second, third, and the
Okay.
rest columns, these are basically the features: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So total 13 features are there. Total 13 features are there, and what are those features we will see. But you need to understand that there are 178 data points in this data set. There are 178 samples, and there are three classes in which you have to divide. Basically, whenever given the 13 feature, you have to tell which of these three wine is there. You have to predict that. Good enough?
Oh,
Now
okay.
what
Yes.
we will be doing, we will be seeing these data, and we will be applying the decision tree and random forest. So random forest, any particular example I have not shown, right? Because
Yeah.
I have told
Yes.
that once I will be finishing the gradient boosting, then I will show you, right?
Okay. Yeah.
Okay. So
Yes.
what I will be doing, I will be uh, taking this data set, and we will perform decision tree, random forest, and gradient boosting. All the three here. Okay. And then you can see and maybe compare, or whatever. You can see how. I mean, the sklearn thing is all the same. So only thing is reading and writing the data and all. So okay, let us start from here. So this is the wine.data.txt data point. Okay. Now here I am reading the data, this CSV file. If you see this file, comma separated features are there. Okay. This function read CSV will read the text file, the comma separated file with this separator into the data. And this PD library is the pandas library. Basically, this is a very famous library for reading comma separated file, or basically data manipulation. For any kind of data manipulation, this pandas is a quite famous library. Yeah. So okay. So import pandas as PD, and now You see, from this PD, I have read the whole data in this data. Okay. Now this data will have how many columns? 14, isn't it? First one is the class
Yes.
and the rest is the 13 features. So the first one, the data which I have read, the first one from the ith location entry, the first zeroth, first column basically, I have kept into Y. You might think, you may think that why, what is this dot values and what is this iloc and all. I mean, you have not seen it yet, because arrays in Python is quite simple and straightforward, just the data and maybe a square bracket and all you could have given. But as I said, we are using a library pandas, which is very helpful in reading, the comma separated file, and in just one line you are able to read it, right? So this
Yes.
pandas has again a this whenever you read a CSV through pandas, it will make a data frame. Now data frame is different from what NumPy we call the matrix is. Data frame is a different category altogether. So it's a different basically data structure altogether. So from data frame, this iloc is a kind of attribute or a function you can say, which can uh, allow you to access any column. And dot values, when you do dot values, it will convert it into NumPy array. So if you want to convert data frame into NumPy array, always remember this dot values. You can use dot values. So that's what I was telling. I have kept the labels into Y and rest 13 features, the whole matrix basically, 178 into 13 feature I have kept in X. Now, what are the class names? Class names I am just giving wine1, wine2, wine3. Features name. Now, that 13 feature which we talked about, these are the 13 features. How much alcohol? What
Okay.
is alcohol there in the whatever 178 data points are there? So, what is alcohol? How much is malic acid? Ash, alkalinity of ash, magnesium, phenol, flavonoids, non-flavonoids, phenol. I mean, what I am trying to say is all these are the features of that wine. Okay.
Okay.
Now what we are doing here, we are doing nothing basically. See, this is just to visualize the data set, just the plotting. Okay. So I think what we will do, we will see till here. How does it look like? Maybe I could have run in this way. See, these are your data points. Wine 1,
Okay.
wine 2, wine 3. Now you will say that, come on, you have 13 features. How can you make a 2D image from 13 dimensional data? You cannot. But if you look at the plotting, if you look at the plotting, plt.scatter, whatever I have done, x-axis and y-axis, if you look at that, I have taken only two features, 5 and 9. Out of those 13, I have taken only the fifth feature, that is magnesium maybe, and the ninth feature,
Okay.
that is maybe uh, proanthracis. So on
Okay.
those two features I can make a 2D, right? So on those two features I have made that image, 2D image which we saw just now. And feature names 5 and 9 is also given. Maybe we should try it once more. See the feature name, total phenols and color intensity. These are the two, see the color intensity and total phenol. On this is how your wine data set looks like. Okay. Now, here what I have done, you can easily see this. This is nothing but a train test split, which I have imported from here. This one, sklearn.model selection train test split. This train test split, I just wanted to show you that also. This train test split basically splits the test 80-20 rule it is doing. 20% for testing and 80% for training. Now I have taken decision tree and random forest. As I told you, random forest is a group of trees, right? A group of trees.
Hmm.
So that parameter you have to pass here. How many trees you want in random forest? So basically you want 10 trees. How many? 10 trees you have given here.
10, but
So
why only 10?
yeah, you can take 20 also. You can take 30 also, but see, it all depends upon decision tree. Sorry, the amount of data you have. Now here we in this wine data set we are dealing with 180 data points only,
Yes.
right? So for one say 160 or 180 data points, 10 decision tree are like good enough to handle. Okay. If you have 10,000 data points, then maybe I would say that suggest that okay, an estimator in random forest, the number of trees required, you can increase it to maybe 20 or 50. Good enough. Now
Yeah.
what I have done, I have done the fitting. I mean X-train and using the X-train and Y-train for both the model CLF and CLF1. I mean the decision tree and random forest, and then this is the once this fitting is done. Fitting means that whole training part which we understood theoretically. Then you can predict your X test through result and result one. And this is the result which I have printed, that how your confusion matrix will look like with the decision tree and random forest. Okay, are you cool? So what I will do, I will do sys dot exit here. Till here we will run and we will see. Can you see that? How many testing
Yes.
files it has taken? 36.
36.
Because it's maybe it's like maybe 80-20 or 90-10, whatever it is. Out of 178 data points, data sets, out of 178, they have
170.
chosen 36 for testing. And through the 80-20 rule, when we splitted it here, the basically the decision tree gives this result and random forest gives this result. Okay, if you can see, the random forest is
Yeah.
giving far better results. See here only two, once this two is there, and in decision tree 2, 1, 2, I mean 5 points were wrong, misclassified by decision tree. Random forest just misclassified these two. Okay. Okay, so I hope you have understood till 70. Now after 70, what is happening? That was 80-20 rule, which was not able to give me a better result, because you see 80-20 rule, anyway you are only testing on 36 data points here. That's not a good number. Maybe you would have tested it to 100 or what. So the here we are using again stratified k cross fold. I mean, in only one program, I mean, in the same program, in a single program, I have done train test split also and k cross fold validation also. So
Okay.
stratified k fold I have taken SKF, and then through that I have splitted like in 10 parts, 9 parts for training and 10 parts for testing, and that will go 10 number of times, right? So, so when you split it in 10 parts, the train index will contain 90% of the data and test index will contain 10%, the remaining 10% of data. Okay. And this is in loop. So every time the 90% of the data will be new. And similarly, the X test. Again, Y train, Y test. These Y test and these Y tests are basically the 10%. Okay. X test and Y test. And X train
Okay.
and Y train are 90%. Now same thing. Again, decision tree train, random forest train, fitting them, again getting result out of them. And this time you are getting the true result. This is in for loop, so you will be going back 10 number of times. Okay, so and every time I am just keeping the copy of confusion matrix in a total mat dt and total mat rf. Okay, because because in each iteration this confusion matrix will be on 10% of data, so 10 number of time it will happen, so confusion matrix has to be added up. Okay,
But
and
why you scatter the data points?
just like that, just to see the data points, nothing more.
Okay.
Yeah,
In ideal
scattering,
situation, do
plotting,
we need to,
those things are
sorry,
just
but
for visualization. Yeah.
okay, in ideal situation, do we need to go for scattering the data points
Do we need to go for?
for real situation? Scattering the data points for random forest.
Definitely, definitely, man, definitely. I mean,
Okay.
in real world, whenever you will get data, the data will be a lot more messy. I mean, these data sets which I am downloading from UCI machine learning repository, these are a standard data set
Okay.
which people have given. People have contributed. This wine data set, some chemistry lab or some from somewhere it has come. So these data sets are
Okay.
even
Okay.
clean. Or in real world, you will get messy data. And I mean any data, any kind of data. If new data you are getting from your um, job or from some real client or something, you need to first understand,
Mhm.
visualize that whether they are actually separated or not. Okay. But the only problem with
Okay.
visualization, I mean, only problem with the scattering is it will work only for 2D. It will work only
Hmm.
for
Yes, 2D.
2D or
Yeah.
max 3D, not more than that. If you have 14 feature, 15 feature, maybe just any two feature you can choose and then you can scatter it. Visualization is very
Okay.
important initially, in initial phase. Okay.
Okay.
So this confusion matrix and the total score, everything I keep on adding 10 number of time, and then I am printing the results of this K cross code validation. So what I will do, I will again remove the system.exit from here and push it maybe here. Now you will see both. See, this was from 80-20 split. which we do
Mhm.
not consider much because it has only 36 file as data set. This is a stratified tenfold validation which we have done. Decision tree, you can see that misclassification are these 8 and 10 and maybe 18. 18 data points are misclassified. With random forest, only 4. Good enough? What is the score? What is the percentage of decision tree?
90.
90. And what is the score of random forest? 97.8. Okay. So random forest is
I
doing
have
what? Yeah,
sorry, I have one doubt.
yeah.
How you say that it is misclassified by looking at data?
You remember we have studied this confusion matrix, and at that
Hmm.
time I said the diagonal elements are. See, when we studied this, you just go back and maybe watch that session where we have discussed confusion matrix and some other precision, recall, and those examples. So when how I am able to say, see, this is wine one, this is wine two, and this is wine three.
Okay.
So
Okay.
how am I able to say is this is like true. This is like on this side you can consider it as a true, and this side I mean true thing, and this side
Mhm.
is the result. So 55 times it was wine 1 and it has also detected it correctly. 65 times it
Okay.
was some wine. This 40 times it was some third kind of wine, and all these time it has detected correctly. 4 times it was wine 1, but it got
Hmm.
detected as wine 2. You understand this?
Okay.
Wine 1, wine 2,
Okay.
wine 3. Wine
Okay.
1, wine 2, wine 3. Now 4 times it was
Yes.
wine 1, but it got
Yes.
detected as
Yes.
wine 2. 5
Yes.
times it was wine 3, but it got detected as wine.
Point two. Yeah.
You got this point of confusion matrix?
Yeah. 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 Now I got it. Yeah.
Yeah. So like that it does. Okay. Now,
Okay.
yeah. So the decision tree basically gave you 90% accuracy and the random forest gave you 97% accuracy. Good enough? And what does this
Okay.
mean? This
Yeah.
means basically that your random forest, this 10 decision, random forest is what? Basically it is made up of 10 decision trees.
Hmm.
But when they are combined together, relying on each other, when you join them, that become a very powerful model. So the 10 decision, now you are relying on basically all the 10 decision trees. So 10 hands are there, and that's
Okay.
why the majority of the decisions are good, 97.8%. Okay. Now, now you may like to see how has it come up. So I will show you. See, this is the wine dataset decision tree.
Hmm.
See this. See, the first one has proline. On proline, it has divided.
Okay.
Proline is what? Proline is one of the 13 features on which it has divided. And the three
Okay.
data, the 162 data point, which it has chosen for training, 80% or whatever, 90%. The values are like this: 54, 64, and like this: 54, 64, 44. These are what? These are third type of wine, this is second type of wine, and this is first type of wine. So these many data points are there of first wine, these many are of second wine, and these many are of third wine. And similarly, so it splits on proline, and then it goes to true, and then it goes to false. So again, then there is some decision, then again, so like that, if you see, here you can see all the this, you see all the leaf nodes are pure.
Yes.
Pure. Only single class. Only
Single class.
single class. Like this is all wine 3. This is wine 2. This is wine 2. Anyway. So that's what I just wanted to show you. And each of these colors are basically telling you the class. So the purple color is saying wine 3. Wine 3. And if the purple color
Yeah.
is very dark, it means, like in here, when it is becoming
Mm-hmm.
very dark, it means that is a pure mode. And in this case, where it is purple but it is very shady, because this is the impure case. Okay, so this also matters. Basically, if you will go through this, you will understand. This is the decision tree. Now, what else? Okay, this was the decision tree. Now, what about the RF trees? I mean, there are 10
Yeah.
this random forest model also, right?
Yeah. Yeah.
So yeah, so what I was saying is random forest. See, this is the random forest. Random forest first tree. So I have fixed the label. We have fixed the label here as 5. 1, 2, 3, 4. 1, 2, 3, 4. Four levels maybe uh, like this has been fixed. Okay, so this is the random forest first tree. Then second tree. Then third, fourth, fifth, sixth, seventh, eighth, ninth. Basically, I have kept all see this one. Again, one, two, three, four, four depth. You have to stop at 4 depth only. And the leaf node, if they are dark, it means they are going to be pure. Otherwise, it will be little uh, shady kind of color. Okay. And how I am able to make this tree in PDF? You see this. This is for decision tree, wine decision tree. Because in decision tree only one classifier is there, no? So you just give the classifier name, it will export the graph, the decision tree. And this is for random forest. So in random forest CLF1, there are 10 estimators. So I am basically iterating through each estimator. Same logic as here. Export the tree and all with the estimator, with each of the estimators, and then try to write the PDF. So do it 10 number of times. Okay. I mean, this is the code for printing, writing that PDF file.
Okay, okay.
Yes. Okay. Now this is random forest and this decision tree. Fine, good enough. Now gradient boosting, can you apply here? Gradient boosting can also be easily applied, right? How? Just
Okay.
make a CLF2 here, gradient boosting, whatever estimator and all you have to give, and like that you can fit here CLF2 dot fit, then result, then maybe add a total mat for gradient boosting, and you can calculate the score for gradient boosting. Gradient boosting will also come around this random forest only. Okay, you need to just check where,
Mhm.
in which of these library that gradient boosting will come. Okay, so let us go for that. Are you able to see the Google? I mean the Google search which I am doing. Hello, hello.
Shown by Google.
No, I was just telling that you can add a gradient boosting classifier like this on the train test split. Then you can fit it like
Yes,
this, predict,
yes, yes,
and then you can maybe print here
yes.
the result here, right?
Mhm.
And you can
Yes.
see with gradient boosting, it's almost similar to what random forest has resulted, right?
Okay. Yeah.
Yeah, it's almost similar to what random forest had resulted, and yeah. So
Almost.
you can similarly
Yes.
apply this gradient boosting here also
Mhm.
in stratified K cross. I just showed you in 80-20 rule. Yeah, you were saying something?
No, no. It's almost all similar. All points are similar.
Yeah, yeah. See, the random forest and gradient boosting, it's hard to say which one will work better.
Okay.
Okay, so sometimes gradient
Okay.
boosting really works very well, and it definitely boosts the accuracy. Sometimes random forest will work very well, and random forest will work generally well. Boosting may sometimes work better than random forest, may not also. So you will find that the accuracies. See here, you see the decision tree is 88% accurate and random forest is 95.5. So there is a clear
Yes.
demarcation that random forest is anyway better model than decision tree. But with gradient boosting, you cannot say that much. Okay, in this wine dataset which I have also tried, it will come out very similar to these result, 95.5 or 96%. Okay,
Okay.
yeah. So the way we have applied here gradient boosting, na, similar way you can apply
Mhm.
this stratified K cross fold. Just apply here, 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 and yeah, that's it. So you can then print these accuracies and all. Okay, for gradient boosting also you can print. You can also print these trees, the graphs like this. for gradient boosting
Okay.
also in a similar manner.
Okay.
The way this has been, this random forest has been printed. Okay.
Okay. Yeah.
Yeah. So this is how we apply all these models, these tree-based models. So these are the majorly, these were the three tree-based structure which I wanted to. Uh,
So can you print the Startify fold validation for gradient boosting like
yeah,
you
yeah,
are doing
yeah,
for
we can
random?
do that. Yeah, we can do that.
Yeah.
If you want, we can do that. Just take variables. We have to take some variable. Like I did for
Hmm.
80/20 for this gradient boosting for this stratified K cross, you have 10 iterations, so you have to take some variables like these, and maybe you have to just grab the outputs and add them up for all the 10 iterations. That is it, nothing more.
Yeah.
See, I have made these two variables for gradient boosting. Now here the gradient boosting training and testing, the same thing will be there. Now here I will just keep CLF2 equal to gradient boosting classifier and estimators equal to maybe 10, or let's say 20.
It will increase accuracy
What?
if I increase the estimators
Uh,
or decrease. So
that you have to check. That you have to check. If you see, if you, that's what I was telling you. If you have more data
mhm.
points, then definitely number of estimators should be high. Even I think
Mm.
10 will
Okay.
also do. I just kept it 20. Maybe
Yeah.
we can check it again on 10 also.
Yeah.
That's what, like, machine learning is more about, applying and checking and, experimenting. You cannot
Mm.
just form one rule that this rule will generally be applied to all the data points. I mean, all the cases. It's not like that.
Okay. Okay.
Total mat GB plus confusion matrix y test comma result 2. Result 2 is for GB, right?
Mhm.
Gradient boosting. Also,
Yeah.
this total GB equal to total GB plus accuracy score y test. Fine.
Yes.
So this will add up for this gradient boosting also, all the 10 confusion matrix and 10 scores. Now here
Okay.
I have to print for this gradient boosting also. Gradient boosting, but here the variable
Mhm.
was not RF, it was GB. And decision tree, this confusion matrix also you would like to print for gradient boosting,
Mm,
right?
yes.
So this is GB,
Yes. Yes. Yes.
this is gradient boosting. Good enough?
Hmm.
Okay. Now let us see. Okay. So decision tree gave you 89%, random forest gave 98, and gradient boosting gave 91 only. Okay.
Yes.
Uh, yeah. So what I can do, if I put it 10 estimators only, then still it has decreased 90. I mean, every time it
Hmm.
is randomly taken. So if I put 100, just like that, just like that,
Okay.
100
Okay.
iterations of, you know, same thing. Basically, on this data set, on the wine data set, random forest is working very well. Gradient boosting
Hmm.
is working little better than the single decision tree. Okay,
Okay.
that's what we have, you know, seen directly by implementing these things. So this was basically the wine data set, and these were the basically features on which these trees will be trained. Whatever n estimators we have given that. So yeah, so this completes all the three decision tree structures, and we have seen the implementation wise also that so random forest is one of the best models I can say. I mean, you can vouch
Yeah.
for this always. But yeah, gradient boosting is also a well tried method, and you must try it also. If you are going for random forest, must go for gradient boosting also, just to look for what happens. Okay, sometimes gradient boosting works very well, and this is a small data set, of course, so it
Hmm.
doesn't matter. I mean, anyway, 91, 95, it's fine. If it is on 10,000 data points, then it will matter. So
Okay.
so okay. So this will
See.
end today's session.